So I would like to address Philip's question that we have large magnitude of data. Well, I guess it just you need to combine lots of diagnostics to 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 understand what kind of diagnostic signal are good or not, and just don't rely on a single diagnostic to make your predictions. And that's my understanding is because it's unlikely that all diagnostic are going to go wrong at the same time.
That makes sense. Thanks.
Okay, let me share my screen and okay. So I was making the slides because you know help me, and I will think about this seminar is about like because I'm leaving Davis, so I'm like just trying to get a little personal. If you so please be tolerable. So this about micromillimeter imaging diagnosis and fusion plasma physics, presented by me and co-author Yilen Xiaoliang Garrett, Xinhang, Taurus Woman. Those are the D30 ECI group, and special thanks to other co-authors and either inside group or outside group. So I like to start with this. Like professor told me that happy teamwork achieves successful plasma diagnostics. So basically, so when I joined the group, I know that there are just two kinds of people two kinds of grad students in the group. First is that you have students at Davis, micro that does microchip, develop micro receivers and electronics. And you have me, that is by far my knowledge. I'm the only person, grad student at Plasma, at D3D Plasma. My job is to assemble and troubleshoot the diagnostic system and do physics analysis. So 2017 is the year that I joined the group, and we realized that you see that there are 6 students graduate from the group. They are all graduate with hypothesis, and Professor told me that okay, generation of students make diagnostics so that they can take measurements at D3D. This is a great opportunity. Okay, I just mentioned that when I graduated 2027, 2021, because of COVID, there was nobody, just a remote bell from Davis so saying that, okay, you're graduate. But the problem is that it seems that he forgot to mention an important difference because at Davis, the students, a grad student, all grad student Davis, they when they graduate, they go to Bay Area. They have Apple, Google. You can end up with like a rich scientist. Well, at D3D, you know where I am. And so this just gave you an idea about I'm basically at D3D, I'm responsible for operating and this troubleshooting this kind of is called diagnostic EC imaging diagnostic system. So it was first installed on D3D. SOC stands for System on Chip. It was then installed 2019. And this is you know. So basically, there were only two grad students in this picture. And you can guess which one does the chip, which one does this. And then you found that I need to mention that this photo, Xiaoliang was also involved in this program. He was there at the beginning. We assembled the ECI diagnostic, but somehow didn't. When we took the picture, he wasn't there. So I have to give him a credit, even though I couldn't find one of him with faces. So sorry, Xiaoliang, this is you, and you're doing the diagnostic. And later, a major upgrade to our system is a remote control system. Basically, with this, you can reduce the labor of running ECI. In my perspective, this is also at least $100,000 invention because now you just need Xiaoliang to operate ECI diagnostic. You don't need two people. Okay. Okay, back to the real story that the macro diagnostic at D3D. And so so basically what I did was diagnostic called EC imaging. It collects radiation called EC radiation. and visualize the 2D electron temperature. So basically you have magnetic field lines, the electron do this kind of spectrum radiation, spectrum motion. The spectrum motion will give radiations. And you use optics to focus those radiations and image on 2D receiver array. And use sensors, electronics, and digitizers. Eventually you can oh, well, thank you for Philip to show your face so that I can see how people react to my presentation. Thank you. And you can have EC imaging. So practically means that we do 2D images of plasma, either absolute temperature, absolute electron temperature, or temperature fluctuations. So on D3D, is ECS particularly suited for studying MHD level fluctuations. So I will later explain what is MHD and what is turbulence. And so basically, if you can, sorry, I need to get something. Oh, sorry for it. I need it's FedEx. Um, then so if you're wondering about EC opposition range, it's 10 to 15 centimeters really, 30 centimeters ploidally. And on D3D, this is where we look at on ECI. Of course, we can ship this array to the core. So ECI is particularly suitable for studying MHDs, 2D fluctuations. So on D3D, we use diagnostics to measure fluctuations. You can use ECI to look at MHDs like alpha moles, islands, sawtooth, elms. Use BES to look at low wave number turbulences or intermediate wave number turbulences like ITG, KBM, TM, MTM. Those kind of turbulences those are acronyms for tokamak turbulences. But just saying that they are of a smaller spatial scale. This is a large spatial scale. So from here to here, you have smaller spatial scale. And if you look at really high wave number turbulences, you'll use DBS, Doppler vector scattering. So we are here. ECI is used to look at MHDs. So this kind of address question of MHDs are islands that can leads to disruptions. MHDs alpha eigenmodes can cause fast electron transport. So if you use ECI, those are physics you can participate. And if you use ECI to predict disruptions, it can because it can measure islands. Okay, so basically I took over ECI 2022 from Elon, and I've been doing research as those. For example, ECI is used to visualize various MHD transit events on D3D. Examples like age-localized mode. Basically, this is the plasma edge, and you can have elms, MHD instabilities doing this kind of interchange dynamics. And you can use ECI to visualize the blobby transport. Basically, you have blobs at the plasma edge. And of course, you can use ECI to visualize alpha modes that does the fast ion transport. And you can use sawtooth visualize sawtooth crash. This is also core instability that reconnections are excited to really transport plasma, to really flatten the plasma profile. What I was assigned to measure, to operate ECI, we were mostly requested for monitor elms, but not these days. But when I operate ECI, it was mostly for elms. So I like to just list examples what we have done. And with the ECI, I was able to help identify this kind of negative trinity scenario, HMHDs, aiming to explain the physics of NT-H transport. So for example, this is a POP paper I published 2023, also an APS invited talk. Basically, we use ECI to visualize this kind of elm structures that happens at the negative trinity plasma edge. Explain, okay, at the negative trinity plasma edge, elms are triggered by interchange time MHD modes. And also this is Tyler Cody. He published paper PBCF 2024, and also APS 2024 invited. He used the data. This is 2023 experiment. he used the ECI system to look at the MHDs, the rotating N equals 1 mode at the plasma edge, the radial structures and plot structures, and conclude that in the baseline shape, this is this is heart rate, this is baseline shape. In the baseline shape, that ECI reveals that it is N equals 1 MHD mode that governs transport at the negative trinity plasma edge. And negative trinity is a scenario where you have an L mode plasma edge, but you still have high confinement. And so that's why I'm saying that pedestal is no longer the sole solution to diffusion. You can have L mode plasma still good confinement. And also like grassy elm regimes, meaning that uh, you have pedestal, but elms are pretty small, meaning that you can have elms happening frequently. That this is elm, meaning that if elms happen very frequently, its MHD instability will be quite weak. So you have less concern of the heat flux, the MHD instability caused to the plasma facing materials. And with ECI, we measure that grassy elms are caused by this kind of rotating structures in electron dynamic directions. And also between grassy elms, you can have quasi-coherent modes that rotate in the ion dynamic directions. And and this also be shown in Chi Chen's APS 2024 APS invited talks. So basically ECI, we use ECI to measure all kinds of elms, the emission behavior at the plasma edge, and perform phasing intuition. Why the pedestal behave this way? Why the elms are small? Why Elmo plasma edge can have how the plasma stay in Elmo? And of course, with ECI, I was able to probe all kinds of plasma confinement scenarios on D3D, like I mode, high beta P, Y passage mode, lithium injection. If you're not from plasma field, basically those acronyms means that different ways you confine plasma. Each of them have different advantages and disadvantages. But regardless, those kind of scenarios focus on how to have a good confinement at plasma edge, but still very, very weak MHD events, like very weak M events. And we use ECI to visualize all those events to see that, and you can see, now you know that for I mode, it is a high N structure that causing the MHD burst at the plasma edge, causing this kind of temperature profile, staying away from major elms. And if in high beta P, you have this kind of modes rotating in electron dynamic directions. So by the way, here the N number is very important because N meaning that the cyclinic structure you have in the of these kind of MHD structure in tokamak. Higher number basically means that you are more likely on the ballooning side, basically triggered by pressure gradient of the plasma. If you're on the intermediate wave number or low N number, meaning that you're mostly likely be triggered by the plasma current density. So in plasma edge, there is strong current in plasma. Current itself can cause MHD instabilities. So by measuring N number, you inform the physics that what kind of modes are really triggering what kind of instability are triggering those MHDs. And with IDD, EDD meaning that it's a ion direction or electron direction. This practically means that if your mode is ion dynamic or is controlled by electron dynamic. This is also important because so by the time you know if this ion direction mode is most likely going to be peeling like if the electron direction mode, it can be for example ballooning mode, it can be microtearing mode. Those kind of modes are triggered by electron motions. Okay, and also ECI measures the MHD turbulence, MHD turbulence. So turbulence are the things that you can have. They're basically smaller scale. They are mild. They can govern the transport of plasma. And in that case, because turbulence are pretty weak, you use coherence techniques that you correlate two spatially different channels and find a signal. So because turbulence is weak, it's typically below the diagnostic noise level. And because our group developed very sensitive diagnostics, our signal level ratio are high, you can find that okay, you can measure turbulences, this kind of turbulence spectrum, a good coherence, and you can validate our coherence with other diagnostics called BES. And this is also published in Nuclear Fusion by Philip Kahamanoff and CJPS 2024 MIT. And also ECI helps to visualize the islands. So if you have an island, you want to know his 2D temperature profile, and so ECI is here, and you can rotate island so that ECI look at the whole shape of the island. So this is QQ surface, and you can draw temperature contours to see that this is kind of the island from changing from O point X1 ECI frame, X point or XO point and O point. So this kind of measurements give you the 2D structure of the island, 2D temperature structure of the island. Why it matters? Because if you want to know if the island is going to disrupt the plasma, you're going to want to understand his temperature structure. Certain temperature structures will, if the island shows this kind of very flattened structure, it means that this island is going to be expanding. Most likely, in a few milliseconds, it can disrupt the plasma. If the temperature profile is, how to say, shows more of a smooth transition, basically it means that the delta factor of the island can be stable, and meaning that this island is going to be, it has been saturated, it won't grow, and eventually disrupt the plasma. So measuring the temperature profile of the island give you some information. This island is going to grow, disrupt plasma, or stay stable. Your plasma stays fine. And also we use ECI to validate some MHD models. So this is the code simulation, and this is what you measure in the experiment, and we found them agree with each other very well. And also you use the ECI to image the sawtooth crash events, basically a magnetic reconnection event in the plasma. And this by Syed Bose present at Magnet US conference, and we are still working with them now to publish good papers. The goal is to find why is the reconnection happening so fast? And what kind of, did you see some two-fluid effect structures on ECI and BES so that you can conclude, you can validate models to explain why the reconnection happens so fast. So because normally reconnections happens on resistor time scale, 10 milliseconds, but on D30 it happens at microsecond scale. What really happened? Is there like decoupled electrons ions causing separate temperature and density fluctuations that you see this kind of quadruple structures? And they are working on it at the moment. But with ECI, they don't need to guess. They can try to validate their model. Okay, and of course, ECI is used to just validate all kinds of MHD modelings. Basically, you run codes to find MHD structures. How do you know if your MHD structures from the code are correct? You use ECI to measure them in an experiment and compare with modeling. And we have been doing lots of work in this aspect. Okay, and that is the ECI conventional capability. Basically, if I were there, people still going to use the ECI for those kind of applications. So those are the things next are about the ideas I developed for ECI, because on D3D, people use diagnostics for a variety of reasons. So to survive in this kind of environment, you really need to have some new capabilities to measure new quantities and be helpful to their experiment to measure unique physics parameters. And so I've been trying to develop new diagnostic capabilities from the ECI diagnostic. So, so I would like to say that ECI is characterized as fluctuation diagnosis on D3D, but I try to correct that opinion that ECI is more than a fluctuation diagnostic. It does not only measure MHDs and turbulences, it measures a whole bunch of other things. For example, it measures absolute electron temperature. It measures the internal 3D structure of the plasma, and it can measure the supersome electrons and thermal tail electrons populations, and can measure the runaway electrons, basically are high energy electrons in the plasma. So these kind of applications really focus on the equilibrium and plasma kinetic effects, no longer just the simple MHD and turbulence fluctuations. So this is one example where you use ECI, that you need to use ECI. At least you need ECI for those experiments to be possible. These are low BT experiments, basically because D3 has ECEs, but it doesn't cover the very edge region of the plasma if you have low BT for the field. So in this case, you need to use ECI because it has a larger dynamical range. We can look at the plasma edge. And then when you have some grassy elms, basically you have elms on the D alpha, and you don't see some correlation on the ECE. Basically, you cannot use ECE to study the temperature transport or the heat transport at the plasma edge because it has limited spatial coverage. But with ECI, we can cover the very edge of the plasma. You can see clear correlation with the alpha. Whenever we have the alpha rise, you have a ECE temperature drops. And also another way is this kind of, we call it 3D ECE. And 3D ECE is usually measure the plasma internal 3D structures. So we all know that this Pokemon is a 2D structure. Basically, you have everything is the same on this cross section, and you have them everything that is the same on toroidally in this direction. But that is not true because islands, for sure, lock modes and RMP response are cases where we have a 3D structure. Basically, toroidally, the plasma are behave differently. And it's important to detect those structures and provide those kind of model validations. And on D3D, we use ECI at this toroid location and EC at this toroid location to measure the internal structure of the 3D structure of D3D, meaning that the plasma is no longer toroidally symmetrical. A good example is like here. And this is how you can see that plasma is really toroidally not symmetrical. So when you apply RMP, it's an external magnetic perturbation. RMP is like you apply external magnetic perturbation, and you can create 3D structure in the plasma. And people believe that this 3D structure should be weak, but not according to our measurement. This difference can be huge. That can have 100 eV of difference between the plasma here and here. They're both at the same flux surface relocation, but very, very different electron temperature when you turn on RMPs, meaning that the plasma is really 3D structured. And also, this kind of technique, this kind of 3D technique, robustly informs the bone lock island. So why it is important? Because if you have a temperature profile like this, if you use your EC diagnostic to measure temperature profile, this is rho, this is electron temperature profile, how do you know if you have an island here? Because in your reactor or in any operation, you want to know the island as early as possible. While in ITER or other large tokamaks, when islands are born, they are born locked, meaning that they don't rotate with the plasma. It's a static structure. It's an internally static structure. So in the future large tokamak reactors, how do you know if there's island? So for example, this is the case that you have island is not rotating, and you have a minor flattening here, temperature flattening here. And how do you know if you have an island? Is it caused by island, or is it just caused by a local turbulence flattening the profile? Basically, you don't know. And you cannot safely say there is an island and we need to do some countermeasures, control or suppress islands. But with this technique, you can easily find that this is an island because this is actually also RMP experiment. if you raise the RMP, you begin to see that the temperature between the temperature are totally different. And this is definitely not a turbulent structure because turbulence will cause temperature flattening to be totally symmetrical. But if it is 3D structure, basically because of island, your island is typically you have mismatch between uh, EC and ECM measurement on same flux surfaces. And this basically inform you that the displace it is larger displacements here, larger mismatch in inner flux surface, less of mismatch in outer flux surface. You can even quantify where the island is. And know for sure this is not caused by turbulence flattening, but caused by island. And the other is supersonic electrons. Supersonic electrons are basically no longer Maxwellian. Electrons are not Maxwellian. They are it can be caused by a variety of reasons. For example, you have reconnection in the plasma. You can generate tail electrons that have high energy away from the bulk Maxwellian plasma, and you can have runaway electrons, and you can have lower hybrid wave heating because when you heat the plasma, those waves will interact with the Maxwellian tail electrons and causing those electrons to become superthermal, become non-Maxwellian. And with the conventional EC diagnostic, you cannot see those superthermal electrons because the radiations, because of the radical downshift and wave propagation, the X mode ECE, which is the conventional EC system, will always absorb the plasma, will always absorb the radiation. But with the O mode ECE, which is I planned into our ECS system, O mode ECE is one module in the ECS system. The radiations can pop through because of the plasma does not absorb the O mode ECE radiation. So in this case, the O mode ECE can measures the relatively downshifted the supersonic electron radiation. And clearly we see some experimental evidence because this is a heat count power. Heat count is kind of the source that can generate supersonic electrons. And the supersonic electrons can cause current drive and can cause some emission instabilities and cause plasma heating. So it's important to validate if there are supersonic electrons generated by heat count heating. And you see that whenever you turn on heat counts, you don't see much of a change on the X mode EC radiation here at rho 0.2, but you see clearly a clear modulation on the O mode EC radiation. O mode ECI radiation, basically because ECI is sensitive to the supersonic tail electrons. And when you turn on heat count, you can see rise on the O mode EC radiation, but not on the X mode radiation. Okay, and so the last is that I developed this kind of I put into a lower hybrid band EC receiver. So basically on D3D that you can have this is standard EC band, also double band ECM band. We measure 100 gigahertz radiation, but those radiation are from thermal electrons. But I developed another receiver which had 2 to 9 gigahertz. This band measures the runaway electrons. Basically, runaway means that you have electron energy is over 3 MeV. And those kind of where high energy runaway electrons have sufficient relativist downshift so that this band of radiation is only sensitive to runaways, not the thermal electrons. And we also did this kind of experimental validation that in this experiment, you have EC radiation. This is a conventional EC system. You cannot use EC to predict to predict the runaways or measure the runaways because before this is no runaway region, this is runaway region. That after disruption, you have both regions strong EC signal. But with this band 8.7 gigahertz, you only see a strong signal after the disruption, after the runaway take over the plasma. So this is the band that that are exclusively sensitive to runaway electrons. And We also use this kind of technique to measure very interesting plasma phenomena. For example, the EC signal and lower Harvard band ECS signal, 8.7 gigahertz, 100 gigahertz, they show very different trends when they are transient MHDs in the runway plateau. Basically, you can have runway rise, you can have EC signal rise, while the lower Harvard band EC signal drop caused by MHD instability events. And sometimes you can have some events that only appear on the lower Harvard band ECS, lower Harvard band ECI radiation, but not on the EC radiation. Here you see nothing, but a lot of structures on the lower Harvard ECI band. So this practically means because this diagnostic signal is sensitive to the around electrons, while EC signal is sensitive to superthermal electrons or the weak thermal electrons. So this practically means that those emission instabilities will have different effects on high energy and low energy electrons. Basically, try to give new physics insights how MHD affect the different electron energies of different levels. Okay, so basically, I would like to say that I was working at D3D for many years, and I tried to expand ECI for a wide variety of measurements, not only for the 2D temperature fluctuation, but also like the low BT pedestal measurement, and also the 3D structures in the plasma that really leads to Lock-Boson disruptions, and also the supernosum electron population. Basically, the electrons no longer Maxwellian. How do you probe those non-Maxwellian electrons, and how do you probe the cyclotron radiations? Sorry, how do you probe the synchrotron radiation currents from using microdiagnostics from runaways? And last is the radiation modeling. Because there's not much time, I like to just keep it short. So basically, we do modeling of all those kind of applications. For example, before 2022, I used EC to measure the plasma shape. Like how do you use EC to measure plasma shape and publish papers, and basically use synthetic EC diagnostic. And also develop my own codes to find how the O-mode radiation and X-mode radiation respond differently to the superthermal electrons. And also use the loss cone maser effect to explain some EC bursts during ELMs, like to inform the loss cone electron distribution. Basically meaning that this is very parallel, this is very perp, and electrons Maxwellian will be here anywhere, but because of the open field line, some electrons are lost. Electrons no longer Maxwellian, and this kind of electron distribution will lead to bursts on the microradiation, and also the lower Harvard band EC radiation from the runaway electrons. So in this band, basically in this band, low frequency band, why this low frequency band microwaves respond only to runaways but not to thermal and superthermal electrons. And I will just list one example in detail and this is only one page. So this is a recent work that radiation modeling is applied to explain the Whistler wave frequency bursts from ELMs. ELMs is the age MHD events. Sorry, I didn't write it out later. So grassy ELMs can displace discrete bursts in the Whistler wave frequency range 2 to 9 gigahertz. And grassy ELM meaning that you have very frequent ELMs. And we'll zoom in this region, you can find that each grassy ELM region, this alpha spike, will lead to several bursts in the Whistler wave frequency range, 3 to 3.76 gigahertz, but not on the 8 gigahertz. And why we don't study it, because Whistler wave is an indication of reconnection and fast electrons during ELM. And if I prove this is Whistler wave, I will be publish good papers saying that okay, ELM has reconnections, magnetic reconnection, and ELM has fast electrons. And fast electron carries most of the plasma current and can pose a strong problem to the heat handling at diverter, those kind of stuff. And developed a synthetic code that used a duct theory by ELM filament to explain bursts. Basically, this is top view of D3D, that you have this kind of ELM filament at positive edge, and this filament will confine the Whistler wave So the whisper wave will get constantly amplified in the plasma edge by the fast electrons, so you see a burst. Okay, so I like to say that ECI is very powerful at measuring emissivity dynamics, most structures, low tensor directions, radial structures. They help to understand lots of Elm experiments in a variety of these three scenarios, like microsecurity, QH mode, I mode, high beta P, RMP, impurity injections, and also powerful diagnostic providing model validations to MHD simulations of sawtooths, alpha modes, islands. I've been trying to use ECI for more measurements. For example, like a low PT field for standard EC at low PT field, 30 EC sim to measure the internal 3D field, internal 3D structures, and OMO EC to measure supersonic electrons, and the lower hybrid band EC system to measure the runaway synchron radiations. And I suppose these roles can help ECI benefit more of this research and be more helpful in the research path forward. Okay, thank you. Thank you.
Thank you, Wayne. Thank you for the very colorful presentation. I learned so much. So, well, it is 1:40, so we have 10 minutes for if any participant have questions. Yeah, you are welcome to hand up. So I will try to. Okay, please, James, Professor James Huang.
Hi, Guan Ying. Thank you very much for a very informative presentation. My question is that if you have your wish, what kind of improved hardware would you like to have? A larger array, more sensitive detectors, or higher frequency detectors? What is your wish?
Thank you, Professor Huang. If you ask different person, you have different answers. But if you ask me, I would like to. If you ask me, I would like the. It depends on application. So you can see that my research is to really build new plasma micro interaction principles and use those principles to physics and diagnostics. So for example, if I want to so this kind of research is at 3 gigahertz, 3.6 gigahertz, 7 gigahertz, 8 gigahertz, right? For applications in this kind of frequency range, I would like the receiver to be relay frequency resolved, meaning that it has very strong, very high frequency resolution. Like for example, your receive not the bandwidth is not only 3.6 gigahertz, but maybe 0.1 gigahertz at a time, 10 megahertz at a time. So that you can really probe into the minor spectrum structures. Like for example, if this kind of instability can cause visceral instabilities, particularly at 3.777 gigahertz. And that informed me that it is a coherent mode, and it is certainly a coherent visceral wave. So I would like to have receivers play with the electronics to have those kind of capabilities, variable receivers. So for example, if you give me a receiver, I can say, okay, today I want to measure at 3.777 gigahertz. Tomorrow I want to measure 3.778 gigahertz. Tomorrow I want to this. You give me this kind of flexibility. You give me this kind of way to tune the bandwidth. This kind of analog system, I would really appreciate. I would appreciate those kind of inventions, a flexible system.
And when you are paying attention on the power measurement rather than the phase, right?
This is only radiation.
Yeah, just the power.
Just power, yes.
Okay. Yeah, what kind of
Thank you, I got it.
And when you pay attention on this one, and what now I know you use some broadband antenna to receive the emission from the entire observation window. So what kind of the front end coupling is your preference? You prefer to have the more direct to the plasma, or have the polarization rotation, or you prefer some just the X mode or O mode?
That's a great question. So why did this experiment? Apparently, I don't have this luxury to choose the polarization or the frequency band or everything, right? I can only use what I have.
Mhm.
But if I have a choice, I would like to focus the plasma, focus the microwave to a tiny spot, to a specific direction that you
Mhm.
can look at radiation different direction from plasma, and the beams are really focused.
Mhm.
And of course, you want to have polarizations that it's measuring only this kind of linear polarization or this kind of horizontal polarization that give you more of the basic information about the radiation. Because right now we can measure only the global radiation.
Mhm.
But if you show your polarization and found, okay, this radiation go away, you can definitely conclude this is external radiation and this is western wave, not other like long wave stuff.
Mhm.
And I would like to say I prefer electronics with flexibility that you can just tune it at a large range for the physics purposes. Because when I do the experiment, I don't know if the wave going to appear at 3.777 or 3.778 or 4.666. Or there, for example, if I want to study the parametric instability from plasma, basically you pump a heating wave 4.6 gigahertz, you see the scatter wave of 4.61. And how can you have a microwave system that can block the 4.6 gigahertz radiation, the pump heating wave, but only look at the scatter wave, like the 4.61 gigahertz, which only 100 megahertz difference, right? Or 10 megahertz difference. So those are the challenges you can imagine for a microwave system.
Yes. So thanks for the question and answer from James Wong and Wayne. So is there more questions? I mean, you may ask questions whatever you want, not only limited on this presentation.
Hi, Guan.
新航, hi.
Yeah, I have a physical question at page 27.
Mhm.
And from here we can see when the magnetic fluctuation begins, we can see the drop of signal at 8.7 gigahertz, but the rising at 112 gigahertz. So what do you think that caused the difference between the two different frequencies?
My interpretation is this. So EC signals, it measures the supersonic electrons, basically meaning that it measures electrons of 100 keV and less. Well, this kind of LHECI, it measures electrons of over 3 MeVs. So when you have a reconnection events or like minor MC events, those high energy runaways, they may just get dissipated by the reconnection events fast. Well, because of the reconnection itself can generate paraelectric field, it can give energy to the low energy supersonic electrons. Hence, you see a rise on the signal of ECs on AC signal.
Okay. Do you think that during the reconnection, the high runaway electron will scatter into the parallel direction to the perpendicular direction? Is that do you think that is one reason?
You are saying that during the reconnection,
Yeah, the scattering is the scattering the direction of the runaway electron to from a parallel direction to perpendicular direction.
so yes, that's I honestly I don't know. I want to use that explanation, but honestly I don't know because wrong way sawtooth is more like a reconnection events. Reconnection events are more like global events. Doesn't really impact the electron dynamics electrokinetic space, velocity space. But sawtooth does generate reconnection does generate a parallel electric field. A parallel electric field can certainly, like you said, drop the pinch angle of the electrons. But I'm not sure it can raise the pitch angle so that you see a rise of the EC signal.
Got it. Thank you. And another
But
question.
that's I don't know. I guess that's up to the theoreticians.
Yeah. And another question is about the 3D structure of sawtooth. Did you check when the sawtooth breaking crashing during the crashing? Did you check the 3D structure of the crashing time at the different toroidal position? Like when the crashing begins, is that symmetric around the toroidal direction or asymmetric, not symmetric?
So those kind of sawtooths will create a MHD burst, magnetic burst on the minerals, and clearly there's an equals one structure, right?
Not sure.
But on the temporal resolution of the ECI and ECE, they happen simultaneously.
Yeah. What I'm saying is the 3D structure of sawtooth, and check with ECE and ECEI, and you can see the phase difference between ECE and ECI. So that must excite some 3D structure in toroidal direction.
I see your point.
And
Unlikely because if that's a 3D case, it will be oscillation. It will be oscillation mode. This is quite equilibrium level that this only happen on slow time scale. A clear mismatch happening over a long time.
yeah.
But if you're talking about 3D structures, it will rotate with plasma at kilohertz levels, and that's not what happened here.
Okay, I see. Yeah. Thank you.
Thanks for the question.
Thank you, Xianhong. So, is there any question about millimeter wave technology or some fancy data importation? If counting once, counting twice. Okay, we just catch it on time, and thanks for all your time, attention, attending for this honor lecture, and thanks again to Gray to have this great presentation. And we hope you have a more succeed based on your current hard working, and good luck.
Thank you. Thank you very much. And also wish best for the group.
Thank you. And